Sure. Let's bring Gaurav to the stage.
All right, let's shoot it out.
Yeah.
Hey,
Hello,
Edson.
Gaurav.
Hey, Karan. Good
Hi,
morning.
Gaurav.
Edson, I think it's good evening for you. Yes, you said or is it late in the night?
It's it's late. It's late. Good evening, I would say. It's 11:30 or almost 12 at
Mhm.
and 12 p.m. And look at how fresh he is. So that's and I'm gonna come to Raleigh and ask you, what do you eat for dinner?
Oh yeah. Well,
Because of your freshness. Because of your freshness, you're still very fresh.
I'm a steak and wine person. So if you come, we'll be more than happy to have you. But if you're a vegetarian, we can find something for you as well.
Thanks, Edson.
All right, Gaurav, the stage is yours. Thank you for coming, and everybody, including us, are super excited to see what you brought us.
Yes, and
this is wonderful.
Gaurav is used to do all of these things. Gaurav is one of the influencer, I would say, on LinkedIn and YouTube. He produced lots of great content around system architectures and Java and algorithms. So Gaurav, you are already a popular star on the internet, and we are glad to have you on the show.
Thank you, Karan. Thank you for making this possible. It's taken a lot of work to make this possible. So thank you both, Karan and Edson. Okay, so let's then start. Today, what I'll be talking about is the evolution of garbage collection algorithms, specifically in Java. But the good news is this is going to be a general topic. I'll just share my screen. Okay, here it is. Right, so my screen is now visible. Okay, so the topic name is the evolution of garbage collection algorithms in Java. But like I said, most of these concepts are actually used in multiple languages. So apart from Python, which has its own way of dealing with garbage, these concepts are used by Go. These concepts are used by a lot of the other languages. In fact, some variations of Python also use the algorithms that we are going to be talking about. Okay. The agenda of this talk is that you understand what garbage collection is, what these algorithms do. So, in case you have some sort of an issue that you're dealing with in production, you should be able to reason your way out, thinking about why did the garbage collection algorithm take too much time, or how can I optimize my process so that I am nice to the garbage collector, which is always running in the background. It's like a big brother. They know you where you are, and they're always in the background. So also, while talking about this, we are going to be thinking about what are the problems that are faced by a garbage collector and how they are solved. And then finally, the GC evolution. This is specific to Java, but we'll try to make it as generic as possible. Okay, who am I? I am the founder of Interview Ready. I have been working with Java for the past 8 years, so I like the language quite a bit. In fact, most of the content that I've created on YouTube, when it needs some sort of a program, I always code in Java. So that's the reason why I like working with Java. Also, in the companies that I've worked in, whether it's DirectI or Morgan Stanley, most of the code that I've written is in Java. Okay, the first problem with garbage collection. When you need to collect garbage, before that, you need to actually identify what garbage is. So there is one specific algorithm for this called the tricolor algorithm. You can think of this as a graph algorithm. Okay, there's three types of objects in your memory. One is objects that you're currently using. The second is objects that you're unsure of, whether using them or not using. And the third one is objects that you're not using at all. So useful, unsure, useless. Okay, and the way we find which objects are useless, which objects are garbage, is by traversing this graph by using a stack. So when you use a stack, it becomes a depth first search. Okay, so let's say our root node is A, and we have A in the stack. Then we find B because it has a link to A. So we are doing some sort of adjacency searching. C comes in. C does not have any outgoing edge. So C is marked as used. Okay, and similarly, we run through the entire stack. But you notice that at any point, we did not touch F and G. So the nodes which are not touched after the completion of the graph run are considered as garbage, which makes sense because if you can't point to it, you can't use it. If you can't use it, it's garbage. So get rid of it and you have freed up memory. Okay. There's a few problems with this approach. There's no problem with the approach, rather, there's a few problems with garbage collection in general. The first thing is when you're doing this, the program is not running. The program has stopped. The garbage collector comes, stops your program, finds out all the garbage, collects it, and while this is happening, all the requests that you're getting in your server are not being handled. Maybe you're running some sort of background process that's also stopped. Everything stops when the garbage collector runs, right? Because it needs its own space. If you are running your program while the garbage collector is running in parallel, maybe you make some extra pointers here, which makes this algorithm not work. You can think of some scenarios where you add a new object to a black object, and there might be a failure. So we'll look into that later in attempts to make it parallel. But so this is a slow process. The garbage is being collected, but we want to make it faster. So there's 3 ways to do this. The first one is to try to identify certain patterns in garbage collection itself. The idea of garbage collection is that you want to take only useless memory. So can you find where useless memory usually exists and optimize there? The second one is to split the graph into regions. Right? This is what we do, whether it is sharding, whether it is taking a recursive approach, any kind of large problem is broken into sub-problems. That's a computer sciencey way of handling things. As you can see, the first one is a bit domain specific though. And the third one is run them in parallel. If you have the number of resources or threads, or if you can run things concurrently or in parallel, usually the process speeds up, latency goes down. While the garbage collector runs for 1 second, the next second you can actually respond to application requests and then again run the garbage collector. So you're time slicing and you're running things in concurrently. Does anyone have any questions till now? What we have done till now is just identified garbage and gotten rid of the white objects. Okay, this looks great. Let's go for step 1. The easiest way, the greedy way, is to identify patterns and change our program according to what the reality is. Right? We find places where we can optimize and then optimize only those places to get the maximum returns. What's one observation that we can have here when it comes to garbage collection? The fact is, just like human beings, if an object has stayed alive for some time, you can expect it to stay alive for a long time. If a person lives for 5 years, then the chance of them living till 70 is quite high. But if the person hasn't made it till 1 year, you're not sure. Okay, that's high infant mortality rate is one way to put it. It's the same thing with young objects. Usually a function needs some objects. The objects are created. After some time, the objects are collected. They're garbage. But if some objects stay for a long time, there's a threshold period, then you know that once they are in this phase, they're probably going to last for a very long time, till this point. And then you can see very old objects are no longer relevant. So sometimes, that's one way that at this phase, maybe you can keep another garbage collecting line. But the idea is simple. You have young objects and old objects. Young people tend to die quickly. Therefore, you should run your garbage collector more frequently in the young object region. Okay, that is the generational hypothesis. How do we use this? We can put a region of young generation and old generation. So that's what we have done here. You're seeing there are some extra regions. We'll talk about them later. Just ignore permgen because that's like permanent objects. More importantly, we have the old generation in blue, which we are ignoring because the rate at which you're running old generation garbage collection is less. Also, guys, hello. I'm sorry. I don't know if I said hi. Thank you so much for the kind words on the comments. And I'll just get to you once we are done with the young generation, old generation fiasco. Okay. So we are interested in the green region because we are usually collecting objects from there, right? And you can see the green is split into 3 regions. Eden comes from the Bible. It basically means that just baby objects, just the start. of the, like when objects are just initialized, you put them in the Eden region. Then you have survivors. You can think of these people who have survived one garbage collection cycle or two garbage collection cycles. All right. So in the start, let's say you have 6 objects which you initialized. This was a function you're running. 6 of them survived, or rather 6 of them were initialized, but only 2 of them survived. So 1 and 5 are survivors. Everything else was useless. You pick it up as garbage. What do you do now? Well, the survivors should be put in the survivor region. Why am I doing this? Because eventually I want to promote all objects into the old region, the useful people, into the old region, so that I don't have to continuously check them and waste my time checking whether this object is alive or not. So I put them in survivor 1. Now some more objects are initialized. A lot of them die rather. And object number 11 is surviving. So I could put object number 11 in survivor 1, but I don't do that, because if I try to do that, then I'll have to find the right place for object 11 in survivor 1, which is its region. If I have 2 survivor regions, what happens is I can easily copy all the objects in survivor 1 and paste them in one place in survivor 2, the live objects. And object 11 can just go and slide onto the remaining objects. So this is efficient, and I can clear Eden, and this can go on happening. So, eventually what happens is, like, an object survives for quite a bit of time. You can say that dark green right now. So object 1 and 5 are deserving of being sent to the next region. You can now go to the old region. Now object 1 and 5 will be assumed to live for a long time. Therefore, I won't check them continuously, whether they're garbage or not. Okay, Rishikesh Devkar has an interesting doubt. What is the frequency of GC run in the old generation? So right now, you can, okay, so firstly, that is configurable. The second thing is, as you'll see, the old generation was usually a stop the world garbage collection. We used to, the young generation is stop the world garbage collection, but you'll see that the old generation also will find some optimizations. Frequency run of old generation is less than that in the young generation. How much less? It can be configured. Okay, you can make it 10x less than the number of garbage collections that you run on the young region. It depends a lot on this graph. If I go back here. On this graph. So it's a standard value in Java. And I don't know the exact value, but looking at this graph, I am sure you can integrate the area of the left hand side and integrate the area of the right hand side and then get a probability. But yeah, that's a good question. Just to keep in mind, you don't want to run your garbage collection process too often. If you run it too often, then your application is not running. You're not serving requests. But if you run it too late, then maybe your application will run out of memory. And the only way for your application to run is to stop everything and run the garbage collector. Okay. As we'll see, the garbage collector should ideally run concurrently. Okay. We are now promoting objects to the old region. This is good news. But the old objects still need some scanning. Okay. And why is this the case? Well, take the green region as the Eden region, or as the young region, the blue one as the old one. We can't simply kill all objects 2, 3, 5, and 6. Why? Because they may have references from the old region. You're seeing that old object 2 is pointing to 3 and 5 here. So collecting them is a mistake, because old object 2 is still pointing to them. And if you refer old object 2 dot 3 dot println, then it's going to throw an exception. Okay, so you need the pointers from the old object to the new object. And the problem is, when you do this, you are effectively scanning the old region also, right? Lots of objects which you don't want to scan because they are rarely garbage collected, but you have to basically scan the entire memory just to see the pointers to the young region. So it kind of defeats our purpose. What we instead want to do is that we want to note down all the pointers from the old region to the young region immediately when they're being made, right? A hash table or a Bloom filter, or some way to tell that this object is marked as alive. So the idea here is interesting. Every time an old object is pointing to a new object, you note it down. How? You use something called code injection. Okay, in Java, you might have heard of .class files. So .class files are assumed to run on any kind of hardware. It just depends on the interpreter. That is what we are taking advantage of. Just in time basically injects some code. Every time you say that old object 2 is pointing to 3, the moment you say that you're pointing to a young generation object, there is some code which runs a if check. If old object in old region and 3 in young region, then add code. What is that add code? Well, you go to the hash map and say that old object 2 is pointing to 3, therefore you cannot garbage collect it. So like a Boolean value, you're just going to mark it as true, 3 is alive. But technically what happens is you're actually using something called a card table, very similar to what we were talking about, a hash map or a Bloom filter. The card table says that old object 2 is an object that you have to look into. Okay, quick recap, this might be going a little difficult. So when you have the young region, having dead objects, you cannot collect them because some of them may be being pointed to by the old region. So they're technically alive. The old region now is split into regions, split into sections, and every section has a Boolean yes or no pointed to it. Okay, 1 or 0. If it is marked as 1, you have to go and check for pointers in the young region from there. So you're seeing 3 here is a section of the old region which has been marked as red, means go through all the objects over there and check if there are pointers to the young region. The way we did this, the way we marked 3 is by actually having a write value. Okay. This is an interesting concept. Let me know if you guys have any doubts on that. Okay, Shishu M is asking, did you ever need to play nice to the garbage collector when you were writing code because the GC was not happy with your code during your office days in DirectIO or some other companies? The strange thing is we were not even coding in Java then. We were using Elasticsearch, which has been written in Java. And what happened is there was a lot of, so Elasticsearch, when you're sending a lot of data, what it does is it updates its tables. So I think they call it segments. But the table updation was so fast, right? Because we were sending data in bulk and in hundreds of MBs or in GBs. So the Elasticsearch was finding it short. I mean, finding its capacity less. Basically, with so many updates, it needs to make a lot of updates to its own table, which results in a lack of memory. So it was basically exploding its table. And then what was happening is it was running a garbage collector. So the garbage collector was trying to find memory because it was short on memory, to the point that it started doing stop the world garbage collection. Stop the world garbage collection basically means that nothing is going to run right now. Everything that we have talked about till now is stop the world garbage collection. We are going to look at how we can speed it up. But the idea is that, if you're running stop the world garbage collection, none of your requests are being met. So our service used to go down. So this was happening in Uber. We were using Elasticsearch, and we learned the hard way that the garbage collector, if nothing else, then the garbage collector will provide rate limiting for you. So I think what happened is we started thinking about how to optimize garbage collection, but unfortunately we should have thought about how to optimize our own program. So we were not nice to it. That was one scenario. Yeah. Rishikesh asks, does the object have some kind of flag that maintains the number of GC that object has survived in the young region before moving to the old region? Yes, there is a counter. There's a counter which tells that how many times this object has actually survived in the young region. So in the Eden, you basically haven't survived anything. Survival region 1, yes, you have a counter. Survival region 2, okay, 2 survivals. And then depends on what you want to configure it to. But after a certain period of time, you're promoted to the old region. Okay, this looks good. Pankaj Agarwal, Eden young object stops everything. Old object do not need to stop everyone. Yes, yes. the Eden, or let's say the young generation garbage collection is a stop the world process. There are certain garbage collectors, I think C4 is one which does young generation also in parallel or concurrently. But the young generation is usually small and there's a lot of garbage. So usually this is a very fast process. The old generation is usually big. So doing garbage collection there with optimizations makes sense. Okay. Ajay Kumar, I think we cannot control the frequency of GC run in young old generation. It depends a lot on factors, including the JVM architecture. That's true. GC is triggered when JVM identifies that young old generation is almost full. We can configure at what percentage we want to trigger the GC, which again is not guaranteed. Absolutely. Yes, that is true. The percentage that you're talking about has recently been, it's not very recent also, it's G1 GC. Since then we have started doing that. So it makes a lot of sense to configure it. But yeah, like you said, Ajay, there's no guarantee that, okay, 60% garbage collector is going to run. It's more like an indicator to the garbage collector that if you want to at 60%, please do the garbage collection. Okay, so let's head to the next part, which is that the generation hypothesis may not be true. Can you tell me one place where the generation hypothesis is false, where young objects usually tend to survive and old objects tend to die? It's a very standard engineering thing that we use, especially on top of databases or on top of expensive queries, where the younger objects tend to survive because they're being used right now, and the older objects tend to die because they're no longer relevant. Any application that you can think about which does this? We usually, to speed queries up, to reduce network calls. Okay, I'll let you guys know. It's a cache. Okay, the cache is a place where you, LRU scenarios. Rishikesh, that's absolutely correct. So Avinaba also has it right. LRU is like least recently used, so it's one policy of a cache. But in a cache, usually there's something like an expiry time, which basically sets a cap. You can't get older than this. You're going to die at this point. So that's pretty weird for a young and old generation garbage collector. Okay, the second thing is that older generation objects tend to die actually really quickly in a cache because they are no longer relevant. So, well, the garbage collection hypothesis fails here. That's one example. The other thing is queue, where you have, let's say, a doubly linked list. So you have a front pointer. Some of these, let's say the 1, 2, 3 are old objects. So initially you push them. So it makes sense for them to go into the older region. Now 3 is pointing to 4. But let's say your front pointer went ahead, okay? And your front pointer is now pointing to 5. The problem is the old generation 3 object is pointing to 4. And because old generation is collected rarely, it means that 3 is continuing pointing to 4. The card table still has that entry. So 4 is still alive and you can't collect it. This is called nepotism, where dead objects or old objects promote the younger objects into the old generation. You can see that 4 is still alive. After a few GC cycles, 4 is going to be promoted to the old region. Okay, even though 3 is dead. The reason 3 is not being collected, like we said, is because the old generation is not collected often enough. So 3 promotes 4, which is dead. Let's say 5 also dies. 4 eventually promotes 5. And so there's this sludge of dead bodies which are being pushed into the old generation and finally collected in the single swoop of the old generation garbage collection. So here the generation hypothesis is again a bad idea. Okay. You can think about Apache Kafka, which handles this. It handles it by using, pages. So there's 2 ways to handle this. One of them is to remove the generation hypothesis. The other one that Kafka, I think, uses is it uses pages of memory, which it can get rid of in one go. So you can have a look at that. I'll add that in the link after this presentation. I'll just share that with you guys. Okay. Step 2, concurrency. ask any engineer how do you speed a process up, and they say let's parallelize it. Usually, domain specific things have been taken care of. Now we are looking for engineering ways to speed things up. Concurrency, parallelization, these are things that we want to do. Yes, the nation wants to know who's at the head of the queue. Nepotism. So, okay. Concurrency is awesome. You can take a process and you can slice it. And then once you slice that task, you can actually give it to different threads and they can do that job for you. We can take this graph, slice it into pieces and give it to different threads, which can find garbage and not find garbage. Okay. Apart from the algorithmic complexity of splitting a graph, the problem here is that we might have something like this. You go to A, mark it as alive. B, C, okay, everything is going fine. C is marked as totally alive, black, because there's no outer node. And here's the interesting thing. Let's say that the application wakes up. Okay, we are going for concurrency, right? Like we want the garbage collector and the application to run concurrently, which means that at any point in time in that code execution, the application can wake up or the garbage collector can wake up and start doing its job without being aware that the other person is actually running. So the application wakes up here. It makes a new object, F. Then it makes a pointer from C to F. And then it kicks out the pointer from D to F. Okay, this is the application doing its job. So the object graph can be manipulated in any way by the application. Now the garbage collector wakes up. Look at the stack when the garbage collector wakes up. B is on top of the stack, right? Left upper side, B is on top of the stack. B now sees that D is alive, marks it. D sees that E is alive, and all nodes are marked except F, which is crazy, right? Because the application clearly said that I'm creating this new object F, and C is pointing to it, which is a live object. So F should have been marked, but it's not. And now it's killed. If you call f.function, it's going to throw a null pointer exception or some sort of an exception. So illegal memory address exception, let's say. Okay, that's the problem. When you're running things concurrently, you might be killing objects which are not being pointed to by any of the unmarked objects in your algorithm. So if a black object is pointing to something, a new object, well, black is already taken care of. So your graph is not going to traverse through the black node again, right? The way we deal with this again is code injection. The problem of losing live objects through code injection can be solved. Let's see how. When you're pointing from C to F, a black object is pointing to a white object. That's the only time this problem happens. If a gray one is pointing to a white object, nothing happens because you're going to go through that node, right? You can see A and B, which are gray, are in the stack. So you're going to go through that node and make sure that all untouched objects are picked up. It's only when black points to white. Okay, so what is one possible solution? One possible solution is to respect the wavefront. Here, I'll just share my screen. Oh, okay. I'm nearly out of time. So, okay. The basic idea is I'll never allow this to happen. Whenever a black object starts pointing to a white object, again, my interpreter is going to see if object equal to black and pointed object equal to white, run the if condition. If condition is basically set the object as gray. Okay, so F is marked as gray. GC wakes up, and now F is on top of the stack. Mark it as black. That's okay, right? The entire subgraph of F is going to be taken care of, and then eventually things work fine. So you don't lose any object. Okay. I'll just check. Karan, is it time? Should I mean, I can share the presentation.
Yeah. So I think, yeah, we can still spend like 2-3 minutes, I guess.
Okay. So I'll just quickly run through the third part because it was talked about as G1 GC. The third thing which we do very often is sharding, split into regions, split into subproblems. Basic idea is you want to partition the heap. You want to mark regions as survivor or old region or young region. you want to remember the pointers with them. So I'll just show you an example which is easier. Look at that. Green is Eden, S is survivor, which is yellow, and O blue is old. Okay. The way this garbage collector works is it works region by region. It doesn't work on the entire on the entire memory, graph. It splits it into regions. Regions are converted to a single region. So here you can see 3 survivors, and a few other old regions are being converted to a single old region. So some survivors are being promoted, while some old regions are being compacted into a single old region. That's the general idea of the G1 GC. Okay, I'll just take one doubt here. Isn't it like this that when all the links to a particular object are not there, even if in the old generation gets collected by the GC? No. All the links to a particular object are not there, even if it is in the old region gets collected by GC. Yes. So I'm sorry, I read that wrong. If it is a garbage object, it will be collected. So the old region object also, if it is garbage, then when you run this algorithm, it's going to give you, it's going to pick up that garbage. On generation hypothesis, this JIT logic is added for concurrency. Yes, usually yes, but there are certain times when you want to add the JIT logic for simplicity also. Deepak Anand is asking, can we talk about G1 GC? Yeah, okay, what are the benefits of G1 GC? I'll tell you. One is that it's incremental. You don't need to run it through the entire memory graph. The other thing is that garbage collection can happen concurrently, which is awesome. And it's easier, so to speak, because it's split into regions. And it also has some advantages like compaction, right? It's taking a lot of regions and compacting it into a single region. So you know where the garbage or the objects are. Okay. The only thing remaining is actually to making that compaction process concurrent. Cool. So those are the 3 garbage collectors we have talked about. The first one was a simple garbage collector. It's basically, it's not even concurrent, right? It's a basic garbage collector, mark and sweep. The second one is concurrent garbage collector, concurrent mark and sweep, which was here. Allows concurrency. The third one is G1 GC, which is pretty good. But there's a newer garbage collector called Shenandoah or ZJC. Those are 2 different garbage collectors actually, but they are also pretty fast. Low latency, slightly lower throughput also, unfortunately, but that's a trade-off. From Java, can you give how object can land to old generation objects? Yeah, like we said, if it survives for a few cycles of garbage collection cycles, promoted to the old region. Pankaj Agarwal asked that question. The example that we said is, if you, let's say, have a object which survives for multiple GC cycles, let's say you create a static object. Although I think that will go in, that should be put in the old region, like regardless, because the static object is just there. Okay. Thank you, Rishikesh.
Yeah, we can see like a great feedback from the questions and from the comments. Yeah, unfortunately, I'm sure we could stay for another hour watching you present this amazing content, but we have to move forward. So yeah, I would like to
thank you so much, Edson. Thank you, Karan.
Thanks, Gaurav.
Thank you for making
session.
this possible.